All right, with this lesson, we start with electromagnetism, and this is probably one of the trickiest concepts for most students to master. We're going to start off slowly. We're going to go through just the general idea of magnetic fields, but then we're quickly going to move into how charges are affected by magnetic fields in the future lessons. So at the beginning here, this video, we're going to talk about all about magnetic fields, where do they come from, and how magnets work. All right, let's start with the basics of magnetism, okay? And so we're gonna start with the things that you're probably most familiar with is permanent magnets. That is the magnets you play with, magnet tiles, magnets that stick to refrigerators, those kinds of magnets. And magnetic fields are created by what we call magnetic dipoles. So what do we mean by magnetic field? So a magnet creates a magnetic field similar to an electric field. A magnetic field is going to ultimately relate how forces act on it, right? Because that's what's ultimately we're going to lead to. But first, you have to understand the shape of magnetic fields. Electric fields, gravitational fields, those fields are a lot easier to understand because of the force. The magnetic force is much trickier. So first, we're going to start about just in general shape magnetic fields. Then we will lead into the forces portion of it, like how do the forces interact with the magnetic fields. So in general, if you take like a piece of a material that can be magnetized, they kind of are broken up into these little domains. And these domains can have different magnetic dipoles. And we usually denote a magnetic dipole as like having a different orientation, like they can point in different directions and things like that. So this would be like you taking a metal like iron. Iron can be turned into a permanent magnet. Okay, but like naturally occurring iron isn't magnetic because all the dipoles, these magnetic dipoles, which I'll denote as arrows, point in different directions. Now, in the presence of a very strong magnetic field, so how do you create a permanent magnet? Is you actually melt it down so these things can rotate. And when you melt it down, you put it in the strength of another magnetic field. I know I'm defining magnetic fields with other magnetic fields, but just bear with me on this. If you put it in the presence of a strong magnetic field and you melt it down, then all of these little domains will then point into the same direction here. Okay? This creates, and then this will ultimately create something that is a bar magnet. Okay? A magnet that is one thing, it's like any of the strong magnets, or it sticks to a refrigerator, things like that. This is where all of those domains are now aligned. All the dipoles are aligned. And it creates a magnetic field. Now, the magnetic field has a few interesting properties about it will create a magnetic field, which has some really, really interesting properties we'll get to in a second. But that's the basic idea, is that these dipoles will arrange in a way, and then that creates something that has a magnet. Now, in terms of the types of materials that can be magnetized, paramagnetic is kind of weak magnetic. So metals like aluminum, titanium, magnesium, they have a very weak interaction with outside magnetic fields, so you can't really make them permanent magnets. Ferromagnetic, so this is a definitional term, iron, nickel, or cobalt, have a really strong interaction with magnetic fields, so you can make these permanently magnetized. So some metals are better at being magnetic, some are not. It just depends on the kind of metal it is, okay? Whether it's paramagnetic, which is weak magnetic, or ferromagnetic, strongly magnetic. Now, the shape of a magnetic field, magnetic fields are still vectors. Just like electric fields, gravitational fields, they are still vectors. So we want to treat them like vectors. They have a direction and a magnitude. Now, for a permanent magnet, when we have like a north end and the south end when it comes to a magnet, and the magnetic fields go from north to south. Okay, so it'll point like this. Okay, technically, so it'll like go kind of like this. This is the direction of the magnetic field. This is what the magnetic field will look like for a bar magnet. Okay, so something like this. You might have seen pictures of like magnetic fields in like movies and stuff, talking about the Earth has a magnetic field surrounding it. Those are the lines that we're talking about here. They point from north to south. Now, magnetic fields technically have to exist in a continuous loop. So what ends up happening is like it loops around and it actually goes in through here. So magnetic fields have this kind of continuous loop shape. And that's an important fact. This is due to the fact that only magnetic dipoles exist. There is no magnetic monopole. So for electric fields, you have these individual charges, positive and negative charges. They don't have to exist together. You could have just a positive charge by itself. So the electric field can just like radiate outwards from it. Magnetic fields, there's no such thing as a unique, like only a north or only a south magnet. Magnets come in dipoles, di meaning two, comes in pairs. They always have to be like that. The consequence of that is that the magnetic field flows externally north to south in a loop like this, okay? So in the magnet goes south to north, but that's the direction of the magnetic fields. They'll always be in a loop like that, okay? The magnitude of a magnetic field we measure in Teslas, and we usually use the letter B to denote the magnetic field. So this is Teslas, okay? Not like the car, but named after Nikola Tesla. Like most units, you got to be a famous physicist in the old days, and then you get units named after you, okay? So let's talk about the Earth's magnetic field. Earth's magnetic field is kind of interesting. Like if you think about the Earth as a North Pole and the South Pole, right? Where Santa Claus is up here, right? Santa is up here. The Earth's magnetic field is actually, but the so this is called polar north or geographic north. That's like how we think of north and south, like on a geographically. However, it's actually flipped magnetically. The North Pole is on this side, and for the magnetic field. So the magnetic field on the Earth actually travels like this way, like this, from north to south, like this. So kind of a little bit backwards. This is important because that's why a compass always points north. If I take something that is like a compass here, as a piece of metal that can orient in a way, it will try to point in the direction of the magnetic field. So it will align its dipoles to align with the magnetic field. That's why the magnet will always point to geographic north, okay, even though it's magnetic south. Okay, so I just want to point that out. Points in geographic north because the Earth's magnetic field actually flows this way from south to north. And that's because the magnetic north is actually in the South Pole. It's reversed. Periodically, it actually switches on the Earth. So super weird when it switches again. Compasses aren't going to work. They'll start pointing south instead. But it's over long periods of time, it will reverse. Okay, so that's the beginnings of magnetic fields. And next we'll talk into how this relates to charges and stuff, which is why we call it then electromagnetism. If you found this video helpful, come check out our school community. It's got an amazing bunch of features. It's got extra videos, corrected videos, better than the ones that I have errors on YouTube. It's got multiple choice free response questions. I hold live Q&A sessions and go through more problems and and I answer students' questions, help with schoolwork, all kinds of things. If you want to check it out, look in the description below or check out the website and find us in the school community. You get a 7-day free trial to give it a shot, just to check it out, see what it's like, come join some calls, and honestly, come learn AP Physics 1 even faster with us.